This is lecture number 22 of the course ME314 Fluid Mechanics 2, and this is the first lecture of this week. We already have discussed about the Euler equations of Turbomachine, and today we are going to see that the first is the velocity triangle, and then we will go into the velocity triangle. There are two assumptions. One is no shock and no prevail condition that is to be utilized in most of the problem solving. And then we will go into the effect of the blade angle on the performance parameter, the head developed or head required in case of a pump, and head developed in turbines. There are typical performance curves, characteristic curves of a centrifugal pump that we will discuss, and then we will see in the end the effect of the blade angle on the different performance curves. So this is a typical velocity triangle for an impeller, and these black lines are actually the blade profiles. And R1 is the radius at inlet, and R2 is the radius in outlet. And you see here at the outlet, this is a tangent line. Similarly, at the inlet, you have a tangent line. So B1 is actually the blade angle, so this angle which makes with the tangent, so that would be your blade angle at inlet. Similarly, this blade makes a tangent at the tangent, and this blade makes an angle with the tangent would be the blade angle at the exit. And this one would be the direction in which the fluid tries to enter. So V1 is the velocity of the fluid, absolute velocity of the fluid, which is the fluid velocity relative to the ground. So that is the absolute velocity of the fluid. But due to that blade which is in motion, so there is an anti-clockwise rotation of the impeller. So U1 is the blade velocity at the inlet. So eventually the fluid enters the blade passage relative to the blade speed within speed of W1. So that is actually the relative speed, and this relative speed makes some angle with the tangent when it enters to the blade passage. We call it B1 prime. So beta 1 is actually this blade that makes with the tangent. That would be your blade angle at the inlet. So that is the blade, and this is actually when the fluid enters to the blade passage. So this beta 1 prime would be the angle to the tangent, what the relative velocity at the inlet makes. So the same is true with that the relative velocity which makes an angle with the tangent would be beta 2 prime, and beta 2 is actually the blade angle which the blade angle makes with the tangent. That would be the beta 2. So the rest of the things are the same we have already discussed. For example, this velocity of the fluid leaving the impeller would be so this velocity of the fluid at the exit is divided into two components. One is in the radial direction, other was in the tangential direction. So the radial component is VR, and the tangential component is V theta 2, and tangential component is parallel to the blade direction of the blade speed. So the rest is the same as we already have done. We have talked about beta 1 and beta 2. Now we are talking about beta 1 prime and beta 2 prime. If we see this velocity triangle at the inlet, in some applications, this blade angle beta 1, this blade makes with the tangent actually meets the relative fluid velocity tangentially at an appropriate angle of incidence for this aerofoil section. So this section is actually called an aerofoil section. So here we can assume that this beta 1 is same as beta 1 prime. So that would be that assumption is actually called as no shock condition, and it means the beta 1 is same as beta 1 prime. So we call that condition to be no shock condition, and it is usually used in this blade angle designs, so that when fluid tries to enter into the blade passage, so the losses to be minimized in that case. There is another assumption we take with the velocity at the inlet is most of the time what we usually do is this velocity of the fluid, this alpha 1 is usually at 90 degrees. So V1 is same as VR1, and so this small v theta 1 component was negligibly small, so we take it that condition is actually called as no pre-weld component. So then we can think of the V1 is same as VR1 and V theta 1 is 0, and that is only possible when alpha 1 takes it to be the value of 90 degree. So these two assumptions, no shock condition and pre-welds, are usually taken in the problems related to the turbomachine. We see this impeller, and we see the performance parameter is from Euler equation of turbomachine, which is the magnitude of the power either given to the fluid or extracting from the fluid, depending upon the difference of the product of the blade velocity times the tangential velocity at the exit and at the inlet. So if the velocity at the exit is some number which is much bigger, so it means the blade has actually imparted energy, so the velocity at the exit is much greater than the velocity at the inlet. So in that case this power output taken to be as positive, and so that is the situation usually happen in this turbines. And if your magnitude of U2 V2 is smaller and U1 V1 is bigger, so then this number comes out to be negative. So it is something to be when power is consumed by the device, so it is energy is consumed in that device. That usually happens in pumps. So for simplicity we take that assumption of no weld component 0. So if V theta 1 is taken 0, so our Euler's equation of turbomachine is a simplified form that is only depending on the tangential velocity component at the exit. So if we substitute some of the geometric factors, let's say we have that V is the absolute velocity and alpha is the velocity of the fluid that makes with the tangent, and W is the relative velocity, and that velocity component is divided into radial component and tangential component. So you just take an trigonometry, this tangent of beta would be perpendicular in base. This base would be the U minus V theta. So this distance is actually the base. So the whole length is U, and if you subtract by V theta, you are going to get tangent of beta. Okay, so we can write, we are on the left hand side and everything on the right hand side. So I can do it, 1 upon tangent would be cot of beta. So I can see that the tangential component is the blade speed minus the radial component of the velocity times the cot of beta. So I can substitute V theta back into that equation. So here V theta 2 would be U2 minus VR2 cot of beta 2. So I have an expression for power, as I know the power supplied to the pump would be rho g HQ, where Q is the flow rate of the pump and head is actually the supplied to the fluid, head supplied to the fluid. So here rho g and rho g cancels out, so we simplify, your head would be equal to 1 upon g times U2 minus VR2, or If you multiply by u2, it would be u2 square. So your head would be depending upon these two terms. So if u2 is the blade speed, and if the geometry of the impeller is constant, so r is constant, and if its angular speed is constant, then this term would be the constant term. So I just say if the flow rate for this would be, because there is no V1 but there is only VR1, so the flow rate would be, volume flow rate would be the area times the velocity. So area at the blade inlet would be 2 pi R2 B2. So that is, we have seen it in the previous diagram. This one is the B1 is the width of the blade at inlet, and B2 is the width. So the fluid enters in the from the eye and then moves in the radial direction. So here the width of the blade is V1, so the volume flow rate which is entering would be the area times the velocity. So that is what we get here is area times area would be 2 pi R2 B2 at the outlet, and the velocity at the outlet would be in the radial direction would be VR2. So just I substituted the value of Q here, so I can see this equation would be because VR2 cot beta 2, VR2 would be equal to Q over this thing. So the whole thing this term becomes this. So we approximately, when I have to use an approximation in a sense that already we have taken an assumption of no pre-weld component. So V theta 1 is already taken to be 0. So that's why this equation relates how your head varies with the flow rate and the blade angle, because speed, if it's constant, R2, B2 are geometric parameter, they are constant. So we can see that this equation is sort of a straight line. So this would be a constant, and this would be a minus sign, and this term would be actually the except Q, everything would be called as a slope. And so we can plot this straight line. So y-axis would be the head, and on the x-axis we can plot Q. So we will be able to plot that equation. So let's say if we plot that at different values of beta. So as you know, when beta is equal to 90 degree, so it means 1 upon tangent of 90. So that term is gone. So only the head would be constant. So head would be a straight line when your beta 2 is 90. If you substitute beta 2 is 90, so cot of beta 2 would be 1 upon tangent of 90. And this would be 1 over infinity, and so the whole term would go towards 0. So you only end up with one term, that is u square over g. So the head at that point would be u square over g. So for beta 2, when beta 2 is 90, you call such blades to be radial blades, or you have more possibilities. So beta 2 is an angle which is less than 90. So less than 90 means you have some positive number multiply by negative, so you have a negative gradient. And if beta 2 is greater than 90, then in the second quadrant tangent would be negative. So this term would make this minus, and minus would make this slope positive. So you can draw the head versus flow rate for different blade angles. So if you see for radial blade angles, so radial blade angles are such that the beta 2 is the angle which the blade makes with the tangent. If it is 90 degree at the outlet, so this would be the construction of the radial blades, and in that case head would be somewhat constant, because your blade angle is 90, so the head is some constant value. Whatever the flow rate is, your head becomes fixed value. If your blades are backward curve blades means the B2 angle is less than 90 degree. So you have an acute angle, then you have a negative slope. It means as the flow rate increases, your head is going to decrease. In case of the forward blades, your beta would be greater than 90. So it means this thing would be a positive slope, and the as you increase the flow rate, your head is increasing. So this is something so-called creating instability or a surge, which we will see in the next slide. So this would be a typical velocity diagrams at the outlet. So if your blade angle is a forward blade angle means greater than 90. So it means this is a tangent line, so your relative velocity makes an angle of angle greater than 90 degree. So that would be the construction of the forward curve blades. And in the radial curve blades, this beta 2 is a 90-degree angle. And in backward curve blade, this relative velocity makes an angle of less than 90 degrees. So that would be called as backward blade angle. And obviously u is the component of the velocity in the because this is, we are taking it a clockwise direction, so that is in the rightward. So that is the blade speed. So vectorically v would be equal to w plus u. So w is the velocity in the relative velocity, u is the blade velocity, v is the absolute velocity of the fluid. And obviously, as we know that I mean, this would be actually the radial component of the velocity. I have not mentioned correctly here, it should be the VR2 actually. So because that is, the velocity is divided into two components, tangential component and the radial component. So that would be VR2 actually. So your head is some function of flow rate. So at different angles, different blade angles at the outlet, that would be approximately your performance, how your head varies in that ideal case when the pre-will component is 0. If you look at the construction of the centrifugal pump, so this is the cutaway of a single stage suction pump. Like the flow comes in the IFN impeller. So this is the impeller, this is the cross section of an impeller, and flow comes in, and there is a shaft which is rotating an impeller, and then the fluid enters in a radial direction. So here you have a single stage pump. So if this flow rate goes back into another stage, then it would be multi-stage. So we'll talk about later the multi-stage pump as well. But right now it is a single stage pump, and there is only one section. So there is a single section, and the flow comes in at an eye and goes in the radial direction. Typically the schematic looks like this. So the fluid enters with the eye, and that moves in the passage in the radial direction, and then we have this volute casing and the diffuser shape, so which further increases the pressure of the fluid. So this is if you take the cross-sectional view at that point, so this view would be if you are viewing it from that section. So you see the fluid enters from an to an impeller parallel to the axis of rotation, and then it moves in the radial direction. So, and this would be the cross section of the casing. So this is a typical schematic diagram of centrifugal impeller. If you look at the performance curve of this typical impeller, is here you see the head. So as the flow rate is increasing, head is constant, and then further increasing the flow rate. So you can think of this, it should be like backward curve plates, because your head is, as your flow rate is increasing, head is constant and then start decreasing. Whereas this line is representing the power which is required at the shaft to run this pump. So more the flow rate, more would be the power requirement. So that is shown here in terms of kilowatt, and that is in terms of meter cube per second volume flow rate. And the dashed lines are representing typically the efficiency curve. So you see there is a certain flow rate at which your efficiency is maximum. At this flow rate, the efficiency is bit lower, like 60%, and here it is up to 90%. So efficiency is also a function of the flow rate, power is a function of the flow rate, and head is a function of the flow rate. So for the expression for the head, we have already worked out for a simple case in which the pre-built component was 0. So here the geometry of the impeller is fixed. So the dia of impeller is given here as 37.1 centimeters. So that's an impeller dia, and it is running at a speed of 2133.5 revolutions per minute. So divide by 60 to get the revolutions per second. So at that given speed and given diameters, this would be the typical performance of a centrifugal pump. If you see this performance for different blade angles, so you look here, for example, if it is a backward curve blade, so this line would be your head line. So what is actually happening with the backward curve blades, it first becomes constant, and then as the flow rate increases, volume flow rate actually, this volume flow rate increases, the head drops. So, but in case of radial blades, the curve is further increasing the volume flow rate. Head is not constant, but head start increasing and then decreasing. Whereas in forward curve blades, which are having this change of the head, first head decreases and then increases. So this is actually called as surge. So because head is not constant, so we want a constant head. That's why the backward curve blades are better. And if you see the power requirement, because of that surge, and surge is like in a pipe, if there is a change in the pressure or a head is there is a pressure head associated. So that head, if it fluctuates, first decrease and then increase, that is actually called as surge. So that's why the power requirement for forward curve blade is higher than the power requirement for backward curve blades. So actually we can use different types of blades depending upon the different applications for pumps. So but here if you see from performance, the power requirement is less in backward curve blades with the given flow rate, at a given flow rate and head requirement. So these are the typical performance behaviors for pumps when you have different blade angles. So we see here, the same thing again. So you see this red, the pink one is actually the backward curve blade. So initially it is constant, and then as the flow rate increases, it starts decreasing without a fluctuation. But in case of forward and backward, so you see there is a decrease and then increase, or there is a decrease in radial, in forward there is a significant decrease in the head initially, and then the head increases and then start decreasing it. So, and typically the power requirement is also less in case of backward curve blades compared with forward and radial curve blades. So the head, when your discharge valve is closed, so the volume flow rate is 0. So such a head is actually called as a shut-off head. So for example, in this backward curve blade, the pink one, so this head, which would be ideally would be U2 square over G. So that head would be called as a shut-off head, because the flow rate is 0. So that head would be your shut-off head. And backward curve blades are, that's why the most common, and they have least amount of change in the head, turning of the head, which is responsible for the surge. and from construction point of view, radial blades in geometry are somewhat easier to produce, but they have some high pressure rise. Whereas in forward curve fluids, they have nearly constant pressure rise with smaller blade size and high number of blades. So if you are using it forward curve blades, one can use it, but you need to take more number of blades. Then we could have some nearly constant pressure rise. So even though backward curve blade is better here in this graph, but depending on different applications and requirement and a cost, because curve blades require more construction cost because they are complicated in the design. So in some applications where just you're not bothered with the head and the flow rate is not that crucial, so one can have the radial blade as well. So different applications do have different types of blades. So this is where we have finished today's lecture, and we have seen this velocity triangles, and we have seen the velocity triangle at inlet and outlet, and we have seen the typical performance curve for a centrifugal pump, and we have seen that the performance curve changes as the blade angle changes. So in the next class we will do the problem related to this centrifugal impeller. So at this point I close this, I stop the lecture.